Welcome back, folks. We're going to take a look at the role of the ER and the Golgi in protein and lipid trafficking. So let's get going with that. The first thing to look at on my wonky slide here is the idea of trafficking tags. So proteins that are synthesized in the rough ER by translation must be directed to any number of locations in the cell. And so once that protein has arrived at its destination, it's got to be prevented from leaving. And so proteins that are made in the ER contain specific tags or sequences of amino acids or post-translational modifications which tell the cell where that particular protein should be taken by way of a transport vehicle. So a tag can be a short region, short stretch of amino acids. It could be a little hydrophobic domain. It could be an oligosaccharide side chain that's been added by N or O-linked glycosylation, or some other kind of structural feature. As well as telling proteins where they should be going in the cell and helping them be transported there, tags can also be used to exclude proteins from particular vesicle trafficking pathways. There's also some commonality there with how lipids should be sent to various cellular compartments, and lipids are often tagged by the addition of phosphate groups, and a common example there is the addition of a phosphate to the 3, 4, 5 carbon positions of phosphatidylinositol. We're not going to get into that in any more detail. So the sorting of proteins begins in the endoplasmic reticulum and then in the early cis-Golgi network, cisternae. And then there are also mechanisms to retrieve or retain compartment-specific proteins. The final sorting that happens, the final kind of distribution part of the Golgi, is the trans-Golgi network. So there are mechanisms for putting proteins translated in the rough ER in the appropriate transition vesicles to send them to the cis-Golgi network, and then proteins and lipids have to be moved through anterograde transport to the trans-Golgi network, and then they may be secreted, they may be sent off to other locations in the cell. And we've also got to regulate the trafficking of proteins that have been brought into the cell by exocytosis and then moved via retrograde transport back to the cis-Golgi network, or even in some cases back to the rough endoplasmic reticulum. That's all done with these tags, which help the cell to understand where proteins should be going. You can maintain the protein composition in various compartments, and a good example is the endoplasmic reticulum, by preventing some proteins from escaping the ER, and also then having mechanisms for getting them back from the Golgi. So if you think about all that N-linked and O-linked glycosylation that we talked about that started in the ER, the proteins that do that, they have to stay in the ER, and there are proteins likewise that have to stay in the cis-Golgi network. And so you can either retain them there, or you can have a mechanism for bringing them back. And the reason they leave is that when a vesicle buds and takes a part of the ER lumen with it, it just happens to grab some things which it doesn't know shouldn't be going some other place in the cell, so they have to be brought back. So you can either retain or you can bring things back. So some proteins are kept in the ER by a tag called the RXR tag. So that's arginine. X is any amino acid, arginine, and so that's a short amino acid sequence that retains proteins in the endoplasmic reticulum. Although there are cases you find this in proteins that are destined for the plasma membrane as well. An example of a protein that has that is the MDA, an MDA receptor that's involved in mammalian neurotransmission, and so the tag is used to keep the NMDA receptor subunits in the ER until the whole assembly, the whole complex, the whole multimeric assembly of the NMDA receptor has been completed, and then the tag is shielded or hidden, and that allows the receptor to depart the endoplasmic reticulum and be sent to the cell surface where it's going to be required. So that's the RXR, or the asparagine X asparagine motif. So that's a retention tag. There are also retrieval tags. These are short amino acid tags. The one that we're looking at here is the KDEL tag. That's aspartic acid, lysine K, aspartic acid D, glutamate E, and leucine L. And the other one is lysine, that's KK, and then any two amino acids following the two Ks. And some people suggest that those are hydrophobic amino acids, but there's quite a lot of variation in those amino acids following the two lysines. And so these will tell the cell that the protein with this tag has to be returned from the Golgi to the ER, and that means that protein will end up back in the ER where it's going to do its job, and that all happens via transport vesicles. So those are those two tags right there. There's another neat little mechanism that can be used to retain certain proteins in certain compartments. So let's talk about this in the context of the Golgi. All Golgi-specific proteins are integral membrane proteins with one or more membrane-spanning domains. They're integral membrane proteins with transmembrane domains. And the length of the transmembrane hydrophobic region can determine which cisternae the protein stays resident in. So we've got, if you think about it, we've got the cis-Golgi network, then the medial cisternae, and then the trans-Golgi network. And so what you see is that the thickness of cellular membranes increases from about 5 nanometers in the endoplasmic reticulum out to about 8 nanometers in the plasma membrane. And so as the membrane gets thicker, obviously you need a thicker hydrophobic domain to be accommodated in the membrane lipids, in the membrane bilayer. And that's also maintained as you go from the cis-Golgi network through the intermediate cisternae to the trans-Golgi network. The membrane thickness gets slightly thicker. And so proteins can move through the Golgi through the different cisternal stacks, and they'll only be accommodated as long as their hydrophobic transmembrane domain matches the width of the membrane. And once you get beyond that thickness, that blocks further movement or further migration through the cisternal stacks. And so the width of the membrane has to match the width of the hydrophobic transmembrane segment so that we can fit the transmembrane region into the membrane. And if they're too long or they're too short, then the brain migration of the protein through towards the TGN, the trans-Golgi network, is blocked. So there's a neat little kind of biophysical barrier to the movement of certain proteins into certain compartments. So we'll wrap it up there, and got another discussion on trafficking in the ER and the Golgi coming up soon. I'll see you shortly.